Right, here we go again. So let's start looking at the next round of environments of deposition. So we're going to look at transitional or intermediate environments of deposition. But before we go any further, let's have a quick word about today's code word. So the code word for today's lecture is going to be copper, C-O-P-P-E-R, as in the red metal. So that's copper. Please make a note of that because you're going to need it for the code word quiz. So transitional or intermediate environments lie along the boundary between continental and marine environments. So there's a wide variety of sediments in these environments. So you get clastic sediments, you get muddy sediments, sandy sediments. You can get some carbonates forming in these environments, and you can also get evaporites forming. So it's a bit of a mix. So we're going to look at 4 environments of deposition. We're going to look at deltas, estuaries, lagoons, and beaches. So first of all, let's think about deltas. So deltas are formed when a river enters a body of water. Now that body of water can be an ocean, a sea, or just a large lake. And the thing is as we've already discussed, when that river hits that large body of water, it comes to a complete stop, well, a near complete stop. And so as that water decelerates very, very quickly, all of a sudden it starts losing velocity, loses energy, and so it has to start dumping sediment. And it will not only dump the coarser stuff, so it will dump the sands, but it will also start dumping the fine stuff. It will start dumping the silt and the clay. And so deltas are made up of a blend of clay, silt, and sand-sized clasts. Now, trying to identify a delta just by looking at a few layers of rock is nearly impossible. The only way to actually identify a delta is by looking at a substantial package of rocks, and a delta will produce a very, very distinct sequence within that package of rocks. So the first thing is don't go thinking you can just look at a few layers of rock and go, aha, it's a delta. No, identifying a delta is a very time-consuming process and takes a lot of work, but it can be done. So in terms of the sediments we expect to find, we expect to find clastic sediments as they are dominated by sand, silt, and clay. Deltas themselves are medium to low energy environments. So when the water from the river hits the ocean and decelerates, well, obviously it loses velocity. So deltas themselves are formed in quite low energy conditions. However, the top of the delta is being reworked by waves. The sediment at the top is being constantly, moved around by tides and wave action. So those are actually moderate energy environments. So a delta has, in the lower and middle portion of the delta, it's quite a low energy environment, but the top of the delta is actually quite a moderate energy environment. So once again, the sediments are going to show that. So that's why it's better to recognize a delta as a larger package of rocks rather than just thinking you can use a few layers to identify a delta. In terms of deltas themselves, we would expect to find numerous fossils and ripples, crossbeds, and graded bedding. There's a whole range of sedimentary structures which we expect to find within delta sediments. Now, deltas are split into 3 distinct groups. The first type of delta is what's referred to as a stream or river dominated delta, and the classic example of that is the Mississippi Delta. So here is the Mississippi Delta. You can quite clearly see the delta itself is way, way, way over here, which is quite interesting really when you think about it, isn't it? Because the coastline is just coming around there, and nearly every other delta we know about, deltas, they will form right at the coast. But nope, the Mississippi Delta is all the way out here. So the obvious question is, why? Well, in the case of the Mississippi Delta, the delta itself is depositing sediment at a faster rate than the waves and the tides can redistribute it. So the waves and the tides are desperately trying to carry the sediment away, but they just can't do it. There's too much of it. And so what happens is the delta keeps dumping more and more and more sediment, and eventually the delta just keeps coming out and out and out and out. It just keeps growing into the Gulf of Mexico. And it's going to keep going for as long as it possibly can. And so river and stream dominated deltas form in environments where we have a river depositing huge quantities of sediment combined with quite weak tidal and wave forces, and that will allow your delta to build out into open water. These deltas are also sometimes referred to as bird foot deltas because of their rather distinct morphology. Our second type of delta is a wave-dominated delta, and the classic example of this is the Nile Delta. So we can see here's the Nile River coming up through Egypt, and the Nile Delta itself is this green area here. And what's happened is the delta's built out, and eventually the delta itself has become level with the coastline. And when it's become level with the coastline, it's been exposed to wave action from the winds moving across the Mediterranean. And you'll notice that what's happened is sediment is being taken off the front of the delta, and it's being transported by the winds, by the tides along the coast here. So what we have is a situation where fresh sediment is deposited, it's instantly picked up and taken away. So this means the delta can't build out any further. It's reached its maximum size. And as long as the tides and waves and the delta and the amount of sediment being dumped by the delta are in equilibrium, the delta is not going to change its size. You can see in this case the sediment's being transported all the way up the coast here. It actually continues all the way up and it goes towards Syria and Turkey. That's how far this sediment is transported. The final type of delta is a tide-dominated delta. So this is the Ganges Delta right here. Now, in the case of tide-dominated deltas, what happens is your delta will get covered over by water for a portion of the day, and then when the tide comes back out, it comes off the delta and it pulls huge quantities of sediment off the delta out into open water. Now, what you'll notice is that a lot of these channels are running approximately parallel to each other, and that's because that's the direction in which the tide is moving. So the tide is coming up that way, and then it comes back out that way. And so these river channels within the delta, or sorry, should I say distributary channels within the delta, have orientated themselves parallel with the direction of the tide. And so that's why we end up with this rather distinct looking delta where you have numerous channels all running parallel to each other. Compare that to something like the Nile Delta where you have numerous channels which will fan out. Same for the Mississippi Delta where you can see you have numerous distributary channels fanning out. So a tide-dominated delta will have this rather distinct look where you have several channels running parallel to each other. Okay, so those were deltas. Now let's think about estuaries and lagoons. So an estuary is like a delta formed where a river meets the sea or a large body of water. Now the water in these estuary areas is typically brackish, so relatively slow, relatively gentle. Now in contrast, a lagoon is formed when you have a body of water which is cut off from the ocean by some kind of barrier. It can be a beach or maybe an old coral reef that's been taken above sea level. Now this means your lagoon is obviously sheltered from your ocean because you have the barrier in between to protect it. So you end up with your own little ecosystem in your lagoonal environment. So once again, it's you're going to be distinct, so you're going to end up with distinct rock types forming. In terms of the rock types we're going to get, well, we're going to get mostly mud-dominated sediments. So lots of clays. You can see, you can see all the muddy sediment here in this estuary, and this area here. Once again, we're going to get lots and lots of clays and silts forming. In terms of what type of fossils we expect to get, we expect to find lots and lots of burrowing mollusks, crabs, sea urchins, all in these kind of areas. They're all going to leave their burrows within the sediment. We're going to see lots of biotubation, the sediment being turned over as animals burrow through it. We're going to see ripple marks, especially in the estuary sediments, because the wind is going to blow around any water that's in the area, and it's going to produce ripples. And we are going to see some laminations, these very, very fine layers in sediment, but they won't normally be that great. In terms of the environments themselves, lagoons are normally relatively low energy. Estuaries can be between low and moderate energy. And in terms of both lagoons and estuaries, they are strongly influenced by climate change and sea level, because when the sea level goes up and down, obviously that affects where your estuaries are and where your lagoons are. So this is the Thames estuary from the United Kingdom. So the River Thames is over here to the left, and as you can see, it's depositing its sediment into the North Sea over here. So the estuary itself, obviously, as you can see, huge quantities of mud in the area. And the estuary consists of a mixture of exposed and submerged mudflats, produces the River Thames enters the North Sea and deposits clay and silt-sized sediment. So you can see here we have, an exposed mudflat right there, but you can see we have these extensive muddy deposits around here which are currently submerged. Now, estuaries themselves are often very chaotic because you have a situation where you have a body of sediment which is being acted on by the river. It's also being acted on by the tides, and it's being acted on by coastal currents. So you have these three variables all working against each other, churning the sediment up, moving it this way, moving it that way. So it's rather complicated. Now, the sediments will often display repeated layers, which are caused by the tide. So you can get some layering within your muddy sediment. So, when the tide comes in, it will produce one layer. When the tide goes out, it will form another layer. So, in some cases, we can get these nice rhythmic layers within our muddy sediment, but it's not all the time. In terms of lagoons, well, here's the classic example of a lagoon. This is, of course, Venice Lagoon in Italy. So there's the city of Venice right there. And what do we have? Well, here's our barrier island. So this is obviously protecting the lagoon behind it. So the lagoon is this area right here. What you'll notice is the lagoon has several rivers coming into it, and these will be depositing sediment within the lagoon. Most of that sediment will be very, very muddy, so lots of clay, lots of silt, maybe a little sand. So what else do we see? Well, we would expect to see within the lagoon sediments quite fine laminations. As that clay and silt settles out gently, it will form these very, very fine layers. We would also expect to see in areas of the lagoon which are so full of sediment that the sediment is just below the water level, we would expect to see those areas would become vegetated. So you can kind of see these areas here. These areas here, you're going to have, very, very wet, semi-submerged sediment, and these are the perfect locations for plants to grow. And so you'd expect to see these areas over time become very, very heavily vegetated. And so when obviously these plants die, they will fall into the water, decompose, and maybe, if conditions are right, essentially the plants will use up the oxygen, which means any more later plant material will not decompose, and you'll end up forming coal seams. So in some instances, you can form coal deposits within lagoonal sedimentary sequences, but it's not, that common. Most lagoonal sequences are dominated by clay and silt, maybe a little bit of sand, and within the sediment itself you're going to have lots and lots of organic activity, lots of burrows, the odd plant fossil, the odd freshwater or saltwater fish fossil. Now the lagoon itself is kind of changes depending on what type of lagoon you're dealing with, and it depends on the amount of communication that the lagoon has with the open ocean. So let's look at two extreme examples. So these are the Mississippi barrier islands. You can see here they are all running parallel to the coast there. So here's the Mississippi Delta right there. Now what you'll notice is the area behind here is protected by the islands, so it's technically a lagoon. You'll notice though there are very, very large gaps between the islands. So this lagoon has quite a lot of communication with the Gulf of Mexico. So the quality of the water in here is obviously going to be very salty, because you're going to have lots of salt water coming in from the Gulf of Mexico into the lagoon, creating quite salty conditions. Now let's compare that with Long Island in New York. So here we go. So here are the barrier islands coming along here. See them running along there. So you can see this is the lagoon, or one of a few lagoons. This is the largest one right here. Now what you'll notice is there's only a couple of very small entrances for water from the Atlantic to get into the lagoon. So this means that this lagoon is quite isolated. It doesn't communicate very, very well with the larger body of water here. And so this means the water within this lagoon is controlled by the water coming in from these rivers here. And so the water in this lagoon is going to be a lot fresher, a lot more fresh water in this lagoon compared to the Mississippi barrier islands. So this means lagoons will vary. So there's obviously lagoons in terms of temperature. Are they in equatorial regions? Are they in quite high latitude regions? That's one thing to consider. Then there's also, we have to consider what type of salinity does the lagoon have, and that's obviously going to affect the type of life that we get in the lagoon. Do we get freshwater fish, saltwater fish, etc.? All of this has to be thought about when we look at these sediments. You'll notice, by the way, in the case of Long Island Lagoon, if you look over here, you'll see the lagoon is actually filling up with sediment. It's called silting up. So as the lagoon fills up with more and more sediment, eventually the lagoon becomes completely full, and the lagoon has then silted up. So our final environment are beach environments. So beach environments are typically dominated by sands. That's what we normally think of. But beach environments can actually also be dominated by carbonates. So in some instances, you can have a beach that's actually made from particles of bits of shell, or made from small carbonate particles called ooids. So don't always assume your beach is going to be made from sand, as in siliciclastic sediment, sorry. Because remember, sand is a size, not a composition. So the sediments that make up most beaches will be detrital. They'll typically be dominated by quartz, some feldspar, and a few other bits and bobs thrown in. The sediments themselves will typically be relatively free of fine sediments, so clays and silt will often not be present at your beaches. That's because every time a wave hits the beach, it picks up the clay and silt and it pulls it out into the open water. So the clay and silt get taken away. In contrast, you don't expect to find large stuff like cobbles, boulders and gravel at most beaches because it's not a high enough energy system. So that means your beaches will very often be dominated by sand-sized particles. Now, because you're dealing with a situation where we have waves hitting the beach, we expect to find symmetrical ripples on the side of a beach that's being hit by the waves. But typically, when you come to the rear of the beach, you can just see it off to the right-hand side of this picture here, there is an area where you have a build-up of sand. Now, this area is not disturbed by wave action, and so the sand in this area is actually moved around by the wind. And so the rear of a beach is very often actually covered in dunes. And if you've ever driven to a beach, you'll know you typically park up on, and then you have to walk to the beach. And as you're walking to the beach, normally you have to go over a rise. And that rise you're going over are actually the dunes at the back of the beach. And then obviously you break over the dunes and you can see the beach itself and you can see the sea. Now, beaches themselves will form along coastlines anywhere. And beaches will often display crossbeds, symmetrical ripples, obviously lots and lots of shell fragments. This is the way that we tell the difference between a beach sand and a desert sand. You do not expect to find pieces of shell fragments. You do not expect to find shell fragments in a desert sand. You do expect to find shell fragments in a beach sand. Okay. So now let's think about marine environments. So these are the environments which spend their entire time covered in seawater. So these environments include the continental shelf, the organic reefs, submarine fans, and the deep marine environment. Now, just going back for a second. These environments are often relatively low energy. So as you come away from the coast and you go into deeper water, the energy gets lower and lower and lower. So if you want a relatively high energy marine environment, you need to be near the coast in most cases. The deeper the water gets, the lower the energy becomes. Okay, so in terms of marine environments, well, shallow marine environments are formed between 0 and 200 meters water depth. That environment is referred to as the shelf. And the shelf is an area of continental crust that's covered by seawater. As you come to the edge of the continental crust, you drop down. The edge you drop down is called the continental slope. And then when you come off the continental slope, you come onto the deep marine environment or the abyssal plain. That is underlain by oceanic crust. So it's oceanic crust here. This is the edge of the continental crust, and the shelf is continental crust. So the shelf is typically between about 0 and 200 meters water depth. And some examples of environments that are marine would be reef environments, deep sea environments. Now, barrier islands, offshore environments, deltas, tidal flats, beaches, they are all intermediate environments because they will be exposed during portions of the day and covered by the sea at other times. So, though we're going to think about four environments of deposition for the marine setting. So we have shallow marine, clastic, carbonate shelf, those are chemical, continental slope, clastic, and deep marine, also clastic. So shallow marine system. So let's just keep going. So here we go. So here are our marine environments. So once again, we have our continental shelf, which is essentially underlain by continental crust. We have the continental slope, which is the edge of the continental crust. And then we have the abyssal plain and continental rise over here. This is oceanic crust. So we can see, if you look at this diagram here, that every once in a while there will be a landslide that comes off the continental slope, continental shelf, and comes down the continental slope and deposits sediment at the bottom here. And this buildup of sediment will produce what's referred to as the continental rise. So you have the continental shelf, the continental slope, the continental rise, and the abyssal plain. Continental crust, underlain by continental crust, underlain by oceanic crust. Okay, so let's think about shallow marine environments to start with. So shallow marine environments, well, obviously are going to occur just off the coast in 0 to 200 meters water depth. Now, these environments are very, very rich in life, so sediments formed in this area are going to be absolutely stuffed with fossils and burrows and other indications of life having been in the area. You are going to get a mixture of both detrital, so clastic, and chemical sediments, if the conditions are correct. So off the coast you expect to find sandstones and mudstones, and in some cases you can also find carbonates forming, limestones. Typically, as you come off the coast and go into deeper water, you expect to find sandstones closest to the coast, followed by mudstones as the water gets slightly deeper, and then finally followed by carbonate sediments as the water gets even deeper still. Remember, only 0 to 200 meters depth though, so it's quite shallow. The environments themselves are typically medium energy. There's lots and lots of wave action churning up the water, there's tidal action, there's currents, there's storm action depending on if there's a large storm coming in. So these tend to be relatively moderate energy environments, and because there's lots of water moving around, that means you get lots of things like ripples. You can also get some dunes forming. So just in the sandy area just off the coast, if there's things like strong currents that are moving in just one direction, you can actually end up forming submerged dunes. And obviously, as discussed, you are going to find lots and lots of fossils, and you are going to find lots and lots of biotubation. That's the process by which animals churn up the sediment. Now, in terms of the carbonate shelf, so carbonate shelves are areas where you have carbonates dominating over clastics. So the classic example of that is somewhere like the Caribbean. So carbonate shelf environments will produce large quantities of limestone. You expect to find reefs, and you expect to find build-up of carbonate particles behind those reefs in the protected areas. So most of the sediments you're going to get in this area are going to be chemical, and they'll very often be quite fossil rich. Now, the reef itself will be quite high energy, but the area that's protected behind the reef will often be quite low energy. Now, the build-up of carbonates is quite nice because carbonates will tend to form under very limited conditions. So this means that when we find a carbonate, we can typically say, right, this rock must have formed under the following conditions. So in order to form limestone in large quantities, the water typically has to be clear. It has to be shallow, that's 0 to 200 meters water depth. It has to be warm, and normally the water is 30 degrees north or south of the equator. And so if we find a limestone in our sequence of rocks, we can, in a lot of cases go, right, we found the limestone, therefore we know it has to have formed in an area that meets these criteria. Obviously, loads of fossils. We expect to find absolutely piles of fossils within most carbonate sediments. And obviously the fossils are going to give us a good clue about where we are. If we're finding, large quantities of coral fossils, well, clearly in bryozoan fossils, we know we're in a reef environment. Obviously we'll find freshwater fish, we'll find sea urchins, we'll find, other materials which are telling us we're in the marine environment. And so, it's quite easy to pick out a carbonate shelf. So there's a couple of different types of carbonate shelf. So this is the standard carbonate shelf. This is the kind of thing we have in areas like the Caribbean. So dry land over here. Here's our lagoon, and here's the reef at the edge of the shelf. So the reef will form right at the edge of the continental crust, right at the extreme outer edge, before the crust just starts to dive off and become the continental slope. So the reef forms right at the edge. Now over time the reef will become larger and larger, and eventually the reef will form a solid barrier, which we call a carbonate barrier, and that will protect an area of water directly behind it, which is the carbonate lagoon. And that's the area in which we get these large quantities of micrite forming. If you remember the previous lecture, we discussed micrite, this microcrystalline calcite, or lime mud as it's also called. And you'll get large quantities of this micrite forming back here in the lagoon. You'll also get other things like ooids forming. And so you get a very, very distinct series of carbonate rocks back here. You have very fossil-rich carbonate rocks forming in the reef environment, and you get a whole load of carbonate rocks with lots of fossils forming in this area, which is called the forereef. Now, you can also get isolated environments forming when you have little sea mountains. So a sea mountain, essentially, you get the peak of the mountain just below sea level, within about 0 and 200 meters of the surface of the sea. And so that means you end up forming essentially a circular reef around the top of the mountain, and you end up trapping a lagoon, obviously, in the middle of that reef. And so this is a standard carbonate lagoon. This is what's referred to as a carbonate platform. Just to give you some idea, by the way, of what these reefs actually look like when we see them in the fossil record. Here is a reef from the Cretaceous. Okay, so if you remember, the Cretaceous is when dinosaurs were walking around. This is around the time when T-Rex was strolling around happily. And this Cretaceous reef is made of something called rudists. You can see them here. They're these conical shaped animals. And you can see just, how this reef is a mixture of rudists, which are, in place, and there are rudists which are just piled up all over the place. A coral reef is just new coral growing on top of dead coral. It's just this huge mass of poorly sorted coral material, and that will all become, limestone when it gets fossilized. In terms of the continental slope itself, well, this is going to be an area where we don't get sediment being deposited. It's a slope by its very nature. You don't get sediment deposited on it. You get sediment moving through it. So sediment will come off the shelf here, it will move through the slope, and it will be deposited in the rise down here, or on the rise down here, should I say. So what we're going to talk about now is actually the sediments that are being deposited down here on the rise. Now, these sediments that are being deposited are going to be a mixture of very muddy sandstones. So we're going to end up forming greywackies. If you remember, a greywackie is a sandstone that's very, very mud rich. So the sediments we get down here are going to be detrital. So we're going to get lots of clay, silt and sand sized particles. And they are actually going to be quite high energy sediments, because when one of these underwater landslides occurs, now these underwater landslides are given a special term. They are called a turbidity flow or a turbidity current. When one of these turbidity flows occurs, they are actually quite energetic, and they will deposit a sequence of rocks which is given a very special name. It's called a Bouma sequence. And most geologists will be taught very early in their training what a Bouma sequence looks like, and you'll always keep an eye out for one just in case, because if you spot one, you know exactly where you are. If you see a Bouma sequence, you know you must have been underwater, or should I say, your rocks must have formed underwater down here at the continental rise. Within the sediments themselves, we expect to see some degree of cross-bedding, because remember, it's formed by a flow which is moving in one direction, so we expect there might be the formation of ripples. And we do expect to see maybe some bioturbation, so there might be some indication there are burrowing animals moving through the sediment as well. So what does a Bouma sequence actually look like? Well, here's a beautiful example of one. Just to give you some idea, by the way, there's a coin down there. Okay, so this is our Bouma sequence. Now, Bouma sequences actually have 5 layers, A, B, C, D, and E. However, you can see in this picture here, we only have A, B, C, and D. So E's up here, it's covered by the stones, alas, that's, we're going to have to live with it. So what do we have? Well, remember, this is a mass flow of material coming down the continental slope and hitting the continental rise. So it's been flying down the continental slope, and then all of a sudden the gradient shallows. And as the gradient begins to shallow, the water, of course, loses velocity. And as the water loses velocity, it loses energy. So as the water begins to lose energy, it has to start dumping sediment. And so it starts depositing sediment. So obviously, the first sediment that's going to be deposited will be the coarsest sediment, the sands. So what's it going to do? As it starts to lose velocity, it's going to start depositing the sands, and it's not going to care how it does it. It's just going to dump them. And so it's going to form a layer, essentially, of sand which has no kind of structure to it. It's just been dumped in one go. And that's referred to as massive or graded sands down here. That's layer A. Now, as the flow begins to slow down a bit more, but it starts to get a little bit less chaotic, you're going to get more sand being deposited. Now, the sand that forms layer B, though, is going to have these nice horizontal layers to it. They can be very fine layers, so they're going to be laminations. So layer B is going to be a sand, but we're going to get a laminated sand. Now, as we go from layer A into layer B, and finally we head up into layer C. So what's happening with layer C? So layer C is when the flow is really starting to come to a complete stop. Okay, so let's think of an example. So if you think of water going down a plug hole, so you take the plug out of your sink or your bathtub, and the water starts going down the plug hole, and for a very, very long period of time, it's quite a nice smooth flow of water going down the plug hole. However, right at the end, as the last water starts to go down, the water starts to lose a bit of velocity, and the flow of water going down your plug hole is no longer quite smooth. It starts to get a bit churny, it starts to get a bit chaotic. Now, that's what layer C here represents. It's representing our flow slowing down, slowing down, slowing down, and instead of a nice, neat flow, the flow starts to get a little bit messy, a little bit chaotic. The flow starts to churn up a little bit. And so what that does is it causes the sand of layer C to begin to develop ripples. And so we begin to see ripples forming. We get this appearance which is often referred to as hummocky. We get these ripples forming in layer C. So you can see it starts to get rather uneven looking, quite lumpy. Now then the water velocity slows down even further, and at that point we start getting layer D being deposited. Layer D is dominated by silt. This is showing us the water is really slowing down now. So the water is coming really, really, really slow, almost at a complete stop. Now, because it's lost all this velocity, it now starts dumping the really fine particles, so it starts dropping the silt, and it'll start dropping the silt as nice laminations. And then finally it will drop layer E. Layer E is made of clay particles, so the finest of all the material, and once again it will drop those as relatively, it can show laminations, or sometimes it will just dump them all in one go as a big massive layer without structure. And so geologists will keep an eye out for these Bouma sequences, these layers A, B, C, D, and E, and if we see them, that's really helpful to a geologist because we know exactly where we are in the world. So if we see one of these Bouma sequences, we know it has to have formed down here on the continental rise, so we know exactly where we are. So that's one of the nice times in geology where you know exactly what you're looking at. The final environment of deposition is going to be the deep marine environment. Now, the deep marine environment is obviously a super low energy environment. And this environment is going to be dominated by 3 distinct types of sediment: red clays, carbonate oozes, and silicious oozes. Now, these sediments are both chemical and detrital, and they are very fine-grained and very well sorted. I mean, if you have a look at this picture here, you'll see everything looks quite homogeneous. You've got these different layers, but each layer is quite homogeneous. Now, as discussed, they're very, very low energy, and they'll typically form between about 3,000 and 6,000 meters underwater. So they're very, very deep. Conditions in this area are essentially well below the photic zone. So there's no photosynthesizing life in this area. So these areas are going to be relatively life poor. So there's going to be relatively few fossils. So the sediment that's being deposited in the deep ocean is a mixture of sediment that's come off the land, so it's come off the shelf and come down the rise and continued onto the continentals and onto the abyssal plain. So if we continue back here, it's sediment that's come off the shelf, come down the slope across the rise and has gone onto the abyssal plain. So that's one way that we can get sediment making it onto the abyssal plain. We can also have sediment that's essentially being deposited by dust, being blown off the continents by the wind, just dropped into the ocean. We can have microfossil organisms, so we can have organisms that were living, sorry, give me 1 second, that were living quite happily up here in the upper areas, the upper layers of the water, but when they died, their carcasses floated down to the bottom and got incorporated into deep marine sediments. Remember, these are little microfossils, so these are absolutely tiny. And you get other things, other things being added, like cosmic dust coming in from space. So there's a real mixture of material being deposited. Now, we're not really going to go into too much detail here, but just be aware that because this material is being deposited, and it's being deposited very, very slowly, and it consists of very, very fine material, what you end up with is very, very fine laminations. And this material takes a very, very long time to build up. So deep marine sediments are very often dominated by very, very finely layered, or should I say very, very finely laminated rocks. Sometimes within these sequences we can also get nodules which are made of metal, normally iron and manganese, so we keep an eye out for those as well, because that's another indicator that we might be in a deep marine setting. Alright, so we're going to stop here now and we'll go to the next presentation when you're ready.